Rideout from the University of California, San Diego. Will talk to us about the causal sets as quantum spacetime.
Thank you. I'd like to start by thanking the organizers for giving me this opportunity to speak and organizing this wonderful conference. So I decided, given the limit of time, so I want to give a general introduction to causal sets, but I decided to do it in the context of a particular recent work that I've done with David Meyer. And so I'm going to talk about the causal set program in general, but most specifically the sequential growth dynamics for the theory, which I'll explain in some more detail in a moment. Okay. So I'd like to open just by making a remark about mostly a picture that appears in a paper by Gerard 't Hooft from 1978. So he wrote a paper, Quantum Gravity, a Fundamental Problem and Some Radical Ideas. And so there's a long paper about various things, and then towards the end, he suddenly changes tune and says, well, here's a crazy idea. And he essentially outlines the causal set approach to quantum gravity. And these are some of the arguments he makes. To take the lattice discretization seriously as a model for gravity, the metric tensor is difficult to define on a lattice while respecting covariance. So a simpler invariant concept is that of the causal ordering, or in discrete language, the partial ordering. The partial order can be regarded as defining the lattice itself. And then the consistency with causal ordering of the continuum defines the correspondence between the discrete and the continuum. And he proposes that in the end, we might expect that the early universe emerges from a single discrete element, followed by a tree. And he has this picture of a cosmic tree, which is something growing from some origin element. And we'll see that something rather like this actually emerges from causal set dynamics. Okay, so I'm going to start off with some just general background about causal structures and discreteness and the like. I'll describe the kinematics of the theory of causal sets. I'll describe the dynamics, especially the sequential growth dynamics of causal sets. And then some recent results in showing that there is a dynamical dimensional reduction in the theory. And I want to emphasize that this is a gravitational phenomenon here. So this is not just a purely kinematical construct, but it's really a gravitational dynamical process. And I'll end with some conclusions. Okay, so I just want to, maybe it's not so necessary in this crowd, but anyway, just to step back and look a little bit about the mathematics of causal structures. So in general relativity, we define the theory in terms of a differential space-time manifold endowed with a Lorentzian metric. The Lorentzian metric has null directions, or directions that have distance 0. And so given a point x in the space-time manifold, the null directions then separate the manifold into 3 regions. The future of x, which are those points which are accessible by a future-directed time-like curve, which starts at x, the past of x, with using a past-directed time-like curve, and then space-like, or those points that can't be reached at all by time-like or causal curves from x. Okay, so this defines a partial ordering among the points of the space-time manifold. Namely, we can see here that that x precedes y because there exists a future-directed causal path from x to y. And so we can think of general relativity and the metric of general relativity as giving us a partial ordering among the points of the space-time manifold, assuming certain reasonable causality conditions. So there are many works that have looked at the nature of the causal structure in general relativity. And the most recent, David Malamud, states that the causal structure of past and future distinguishing spacetimes determines the conformal metric topology and differential structure of the space-time. So it's a very rich structure. Furthermore, I'd like to impose fundamental discreteness. These are probably fairly familiar. There's many problems that arise in the continuum, such as divergences in quantum field theory and general relativity, which can be resolved, which kind of arise because of the notion of infinitesimally short distances, and this can be resolved by imposing some sort of discrete structure. So we'd like to formulate a theory in terms of a discrete causal structure, which is a causal set. Okay, so the theory is based on two main observations: the richness of causal structure and the indications of some discrete substratum to space-time. So we define a set. The theory is defined in terms of a set endowed with a partial order relation, which is irreflexive, so each element does not precede itself, and transitive, meaning if x is before y and y is before z, then x is before z. And so this goes by various names: partially ordered set, post-set, partial order, and so forth. But to fully define a causal set, I need to add one additional condition, which is a local finiteness condition, which imposes discreteness. So locally finite means that if you look at an order interval, so this set in brackets, the set of elements y such that x is before y and y is before z, which is sketched here in red in the diagram, the cardinality of this set has to be finite for every pair x and y. And sometimes we impose an even stronger condition, that of past finiteness, such that the past of each element is finite. Okay, so these are causal sets. The irreflexive condition effectively imposes that there are no closed causal curves in the theory. And there's an alternate formulation which is equivalent in terms of a reflexive and acyclic partial order. Okay, so the various definitions of relation is the relationship between x and y. A link is an irreducible relation, a relation which is not implied by transitivity. We'll sometimes use the terminology of genealogy, ancestors, descendants. Chains is a totally ordered set. Anti-chain is a totally unordered set, such as the green elements here. Maximal elements have nothing to their future, so the blue and purple elements are maximal. Minimal have no elements to their past. In the order interval we encountered before, it's for any pair of elements x and y which are related, it's the set of all elements between them in the partial order. Okay, so I've defined a discrete structure. It's a very simple minimalistic structure. Now I need to say something about how does that relate to the rest of physics. So what does this have to do with known physics? And we do that by defining a correspondence with the continuum, a discrete continuum correspondence. The idea is to associate with a microscopic notion of causality the macroscopic notion of causal order in space-time, and with a microscopic notion of number, the macroscopic notion of space-time volume. And so to make this somewhat precise, we define an embedding, which is an order-preserving map from the causal set to a space-time. So order-preserving simply means that if x is before y in the causal set, then their image points 5x is before 5y in the space-time for all pairs of points in the causal set. A faithful embedding is an embedding which is furthermore preserves the correspondence between number and volume. So roughly it means that the number of elements that get embedded into a region of space-time of volume V should be Poisson distributed with a mean of V. And then we need to add a further condition that space-time does not possess structure at scales smaller than the discreteness scale. Otherwise there's no way that the causal set could pick up on structures that are smaller than the discreteness scale. So the discreteness scale is the smallest structure of the theory. Then the statement...
Just a little question. So the idea is that the causal set, the discrete structure is the one that is fundamental, but the manifold structure is the one where we know, of which we know more. So in a sense, this condition is a consistency between what we know from known physics and what we think to be more fundamental.
That's right.
Thanks.
That's right, yes. And so what we're going to say is that if there exists a faithful embedding of the causal set into some space-time, then that space-time is an effective large-scale approximation of the causal set. So right, the causal set is fundamental, and the space-time is some large-scale approximation.
What is the number volume correspondence?
Oh, the number it's this statement that the so correspondence between number of elements in the causal set and space-time volume. For any region of the space-time of volume V, the number of elements which get mapped into it should be Poisson distributed with a mean of V. That's the idea. So counting, you can recover space-time volume information by counting. And it's worth noting that if all we had was the causal structure, there's no way to recover the conformal metric, the notion of local space-time volume, because the causal structure gives us almost all the information, but it doesn't give us the volume information.
So you have the conformal information just by the causal relations, and this gives you the notion of the metric distances is coming from this.
That's right. So this is essentially what gives us distance. So this is what allows us to measure the rate of clocks instead of clocks and such things.
Scale.
It gives a scale, right? Yes. Okay. So so here's some pictures. So on the left here, we have a region of two-dimensional Minkowski space. The blue X's are points in the embedding, and the green lines are the links in the resulting causal set. So this is an example of a faithful embedding. It's easy to construct one. Just take a space-time and sprinkle randomly using a Poisson process. And then the causal relations among the elements are just those inherited from that of the space-time into which it's embedded. And you can just contrast that with the regular lattice on the right. So the red points are the red pluses form a regular lattice in two-dimensional Minkowski space. A problem with this regular lattice is that it's not Lorentz invariant. So if we boost it by some factors, around 3/4, I think, then we end up with this green lattice. And the green lattice is a somewhat terrible approximation to the space-time because there are big open regions with no elements in them.
Sorry, I'm sorry to interrupt, but I never understood that statement that this is not Lorentz invariant. I mean, what you draw in this picture is basically a map from a Lorentzian space-time onto a Euclidean plane. Right? So when you
over here?
Yes. So when you perform a boost, what actually happens is that this map is not sort of invariant with respect to boost, but the Lorentzian, the points are still the same points. I'm not sure if I you can project the surface of the Earth onto a plane, right? But that will distort distances. And when you rotate the Earth and project it again, the distance between 2 points on the map will change. But that does not mean that the distance between the 2 points on the actual sphere changes.
Yes. Okay.
Lorentz invariance is present, but its representation on the picture does not.
Yeah, so let me try to be a little more precise. So on the left here, we're preserving the number volume correspondence. If you take any region here, well, if you take any region before the sprinkling and you can count the number of elements that fall into it, it should be proportional to the volume of that region.
Okay.
While if you do likewise here, if you pick a region, if I pick this region here, or if I pick a region that kind of hugs the light cone, then I wouldn't expect that to be true anymore. And a way to see it is it's true. I mean, the green lattice and the red lattice are equivalent in the sense they're just related by a Lorentz transformation. So in the green lattice, you can see this big open region here, which has no elements sprinkled into it. And on the other side of the boost, that region looks like something long and thin, which kind of hugs the light cone in here. So the point is that the number of volume correspondence is broken here, or it's only true in certain frames, while here the number of volume correspondence is valid in any frame. Okay, so how am I doing for time, by the way?
So you are at 20 minutes now. You have another 10 and 10 minutes for questions.
Oh, okay. All right, so I'll skip over most of these things. There are a number of ways to measure dimension in a causal set. I want to just highlight the Myrheim-Meyer dimension, which is defined on an order interval. So if we look at an order interval here, we count the number of relations in the intervals, the number of pairs that are related. Then we can define what's called the ordering fraction, which is the number of relations divided by n choose 2. And we can compare that with what we'd expect to see if we're sprinkling into Minkowski space, an interval of Minkowski space. And so for a d-dimensional Minkowski space, the expected value of the ordering fraction is given by this expression, f of d. So we can simply invert it to get a crude measure of the dimension of the equivalent Minkowski dimension of the causal set. And this works well for n large compared to this number. Okay. So dynamics of causal sets. So far I've been talking about the kinematics of the theory. I said I would talk about the dynamics. So if we had a classical theory, you could imagine defining a probability distribution. So taking some event D, some set of histories, then we could just add up the probabilities of those histories, and that would give us a probability measure on the causal set. For a quantum theory, we'd expect to do something like defining an amplitude for any causal set gamma. So if we had an action, we could define something like e to the is over h bar. And then we could try to form a measure on that by doing something like, summing the histories for some appropriately defined set of histories. Another way to look at that is with this decoherence functional approach. So it turns out to be difficult to know exactly how to define the quantum measure in this sense. And so what I'll talk about is a particular way of formulating a classical measure, which we may think of as but optimistically we might imagine it to be a classical limit of the quantum theory. Okay, one of the challenges in any discrete theory is that for the most part, there's often any discrete relational theory will often have an entropy crisis of some sort where almost all of the discrete structures are very degenerate objects. So it turns out if you put all the n-element partially ordered sets in a bag and you pull one out at random, you'll almost surely get one that looks very much like this, which consists of 3 layers, n over 2 elements in the middle layer, n over 4 in the top and the bottom, and a bunch of relations connecting them. And so the theory has to somehow pick out space-time-like manifolds, space-time-like discrete structures in the context of this overwhelming majority of non-space-time-like causal sets. Okay, so the sequential growth dynamics, the idea is to grow the causal set one element at a time, beginning with an empty set. The probabilities are based on 3 principles. One is that the causal set grows to the future. 2 is a notion of general covariance, which imposes that the order in which the elements arise in the growth process is a notion of pure gauge. It has no physical meaning. And the third is a Bell causality condition. And so this is a diagram of all the possible ways of growing a causal set starting from a single element. So each upward directed path represents a way of growing the causal set. And then the general covariance condition imposes that if we end up at this element, this causal set here, say we may have arrived from the blue path, we may have arrived by some other path. The idea is that the probability of forming this causal set should be independent of which path we use to get there. And so then it turns out that you can write down a relatively unique family of probability distributions, which are described by some infinite sequence of free parameters, or coupling constants. And one of them is particularly simple, is the transitive percolation dynamics, which is described by a single free parameter p. So transitive percolation is easy to understand. at each stage of the growth process, a new element appears. It flips a weighted coin with probability p. It chooses each element to be to its past, and then it takes the past closure of the set of elements that it chose, and that gives rise to the new causal set. Okay. So transitive percolation has some interesting structures. So one is that it's completely homogeneous. So the feature of any element is independent of anything space-like to it. It's also, probabilistically speaking, it's the same as any other element. Since Carlo's not here, but I'll still point out that it's also time reversal symmetric, which he may like. Due to random fluctuations, however, it appears homogeneous in time. And it turns out that with probability 1, there will be what I call an infinite collection of these things called posts, which are elements of the causal set which are related to every other element of the causal set. So it has an intriguing feature because it seems to describe a universe which starts at a single element and then expands in some way. And if we condition on the existence of one of these posts, that we're looking at the region to the future of a post, we get what's called an originary dynamics, which is almost the same as the transitive percolation, but it just conditions on the presence of a post. And then after one of these posts, the universe expands to exponentially, essentially to a volume of about 1 over p.
Sorry,
Okay.
what is P?
Excuse me?
What is P?
What is p? Oh, p is the parameter. P is this one parameter which describes the transitive percolation dynamics. So it's the probability that you select each element, probability of selecting each element when I add a new element. Okay, so if we look at the limit at which p is small, but we're in the originary situation where we're conditioning on the new element appearing to the future of a post, then you can see that when p is small compared to the number of elements that are present, that each element will choose exactly one ancestor. And we'll we'll end up with a simple model of a random tree. And then we'll get some sort of exponential expansion. And so it's intriguing in that it gives rise to a universe that has some similarities to our own. It's maybe important to note that it's not giving us a space-time manifold. There's various ways we could see that this is not really a space-time, but nevertheless it has some intriguing macroscopic features. So here's a picture of a causal set with 16 elements with p equal to 0.2. Starting from this is the originary dynamics. So the red squares indicate the initial tree region of the causal set. And here's a much larger one with 2,000 elements and p much smaller. So the green tetrahedra here are the initial tree of this causal set. Okay, so I think maybe I'll just skip towards the end here. So how much time do I have now? Including questions?
No.
Oh, okay, great. Okay, so if we want quantum gravity to be asymptotically safe, then we'd expect the operators in the theory to exhibit anomalous scaling at the UV fixed point in such a way that makes the theory effectively two-dimensional. And there's a number of independent lines of evidence that point in this direction. So high temperature string theory, causal dynamical triangulation, loop quantum gravity. So there's evidence from many different approaches to quantum gravity that give rise to something like this. If we look, let's look at causal sets. To what extent do we see this in causal sets? So there have been a number of works in this direction to date. One is by Plencia and Benincasa in 2016. They looked at a non-local D'Alembert derived from causal sets, and they get generically that the dimension approaches 2. However, this is, oops. this is, in a sense, a purely kinematical result. It's based on sprinklings in the Minkowski space, so it's not directly related to the gravitational dynamics. Steve Carlip in 2015 looked at the Meyer dimension of small causal sets. And he looked at 3 different distributions of causal sets. One is just drawing uniformly at random from the set of all partial orders with 4 elements. Second, he's looking at Kleitman-Rothschild orders. And third, he's looking at a causal set sprinkled into Minkowski spacetime, but very small causal sets. And again, he gets roughly 2-dimensional behavior. However, the first 2 are not terribly reasonable dynamical laws. They're quite arbitrary. And the third falls prey to a weakness in the original Meyer dimension formulation. And so it's not so clear what the meaning there is. And so what we'd like to do here is just examine the question in this full classical limit of the gravitational dynamics of the theory. So what does the sequential growth dynamics have to say about the dimensional scaling? So one way to look at this is to look at the future of a single point in d-dimensional Minkowski space and simply measure the expectation value of the number of links to the future of that element. And it turns out that it's not so easy to compute, but it can be done. And it turns out that the expected number of links is given by this formula. It's infinite for dimensions greater than 2, or 2 or greater. And
sorry, is the expected number of links if you do kind of Poisson sprinkling? Or?
Yes, for a Poisson sprinkling, yes. It's one, in 1 dimension, it's exactly 1. Yeah. Okay. So now let's compare this with the sequential growth dynamics. It's important to point out that covariant observables in the theory are based on the presence of stem sets. These are sets which contain their own past in completed histories. So these are histories for which the growth process runs to infinity. So to compute anything physically meaningful from the sequential growth process, we have to run the growth process all the way to infinity. So it turns out that, I don't have a slide for this, but it turns out that for the transitive percolation, that the structure well, because of these posts, this sequence of posts, you can imagine if I grow it far enough that elements that appear to the future won't affect what happens towards the bottom of the causal set. So interestingly enough, you can compute something like the expected number of links from transitive percolation, some infinite sum where n is the stage of the growth process. And so you can, again, get some rather simple expression. And so we can ask, okay, so for some value of q, which is 1 minus p, we can compare the number of links to the future of an element for transitive percolation against Minkowski space, and in that way get an effective measure of dimension. And so just to give some idea, if we want to compare with the observable universe, the value of p, which may have given rise to it, is maybe something like 10 to the minus 84. It's due to Sorkin in 2001. And so we could just imagine, so q is going to be very close to 1. Number of links is going to be huge. If I compare it with this formula, I get something very close to 2. So in this way, I already get an estimate of dimension which is very close to 2. Okay, what about the scaling of dimension with volume? So one way to access this would be to look at thicker links. So for example, we could count 3 chains. So we looked at a single element and its future in Minkowski space, or equivalently in the causal set. So I looked at links, which are suborders like this. I could look at 3 chains, something like that. We could count the number of those. Turns out you can write down a double recursion for the expected number of these 3 chains from sequential growth, but it's hard to convert into a closed form expression. So we have to do this numerically. So just for comparison, this is a numerical simulation of the number of cosmic links as a function of gauge time for 4 different causal sets. And this green line here is the expected value. for a particular value of p. So p is 1 over 256. And n is large enough so that we've effectively run the growth process to completion. This is the mean number of links to the feature of the origin. And we can see it matches the theory very well. So now we can look at something larger, look at these cosmic 3 chains. We can count the number of cosmic 3 chains as a function of gauge time. Again, they plateau for large gauge time, meaning we've reached effectively run the growth process to completion. And we can look at the expectation value of the number of links as a function of gauge time. Sorry, I went the wrong way. We can look at the expectation value of the number of 3 chains as a function of gauge time. And so it plateaus at some number, 18 or so, for 1 over 256. And so on. We can do this for thicker things, so 2 intervals. So we can look at 4 chains, or we can look at diamonds. So this is when I say 2 intervals, I mean either one of these possibilities. And when I say 3 intervals, there's a number of possibilities, but it just means there's 3 elements between the top of the interval and the bottom, connected in any such way. So we can see that the numbers of these things increases with the thickness, what I'm calling the thickness, the scale, essentially, of these thick links.
Is your interpretation then that at late times it behaves effectively like a d-dimensional causal set?
Well, not yet. So at the moment, one thing I forgot to say is that this formula for the expected number of links in Minkowski space also holds for any of these thicker links. It turns out, somewhat surprisingly, but this formula is exactly the same for any of these thicker links. So if we count the number of these, it also, or the number of 4 chains, it also grows at this rate. And so as we increase the scale, we're seeing more of the links or thicker links, and so we're actually, the dimension is increasing and towards 2 in a sort of trivial way. Okay, so we are seeing some increase of dimension with scale. However, it's not quite what we'd like to see. So, right, so an obvious question then is, dimension is about 2 at the small scales. Can we ever achieve a dimension larger than 2? So to do this, we can look at the internal structure of one of these intervals. So what is the effective dimension of the intervals themselves? So, yes? Okay. So because it's a tree, it's 1 at the small scales. But what happens if we look at larger intervals? So here's a 2 interval dimension. Just kind of running through it quickly. So if you look at the intervals with two elements in them, we get an effective dimension of 1.006. If we look at 3, we get 1.106, so slightly larger than 1. Can we ever get larger than 2? Well, it turns out if you look at an interval with 6 elements in it, then you get an ordering fraction of 0.345 and end up with a dimension slightly larger than 2. So it is possible to get a dimension larger than 2 at large scales. And so the picture is something like this. We have, there's 2 notions of dimension here. There's the link counting dimension, and there's the dimension of the cosmic intervals themselves. So in this analogy, imagine that the intervals are like the petals of this, the rose. So as a whole, they give a dimension, effective dimension of 2, but individually at the small scales they're only 1-dimensional. And so we have this kind of picture of the intervals interweaving in such a way that you get kind of 2 different dimensions in the picture. Remember, this is not a manifold, and so we don't expect the dimension to be uniform. And so we're kind of building up something that it may resemble a manifold at large scales. And then if we go large enough that these petals can have an internal dimension which is larger than 2 at large enough scales. Okay. And I'll leave it there.
We have 3 minutes for questions. Yes, Philip, and Marco.
Yeah, so coming back to this whatever dimensional reduction, so usually in most other approaches people study that using the spectral dimension and diffusion processes. How's that related to what you're studying here? Is there any obvious relation? I think Astrid Eichhorn may have studied diffusion processes.
That's right. So there has been analysis of diffusion processes in causal sets. One of the challenges is that the lattice is Lorentzian. So you wouldn't expect the behavior to be the same as in a Riemannian signature manifold. And so you'd have to really analyze the diffusion process in a Lorentzian setting. And so, so in part that's why I've chosen to look at these sorts of methods which don't involve a diffusion process.
Let's go to Pierre and then Marco.
Yeah, I have a second question about in the continuum limit. Should we understand, in fact, the points of the causal set as points of a manifold or as events, which would correspond, for instance, to the coincidence of two particles?
And the continuum limit.
What's a good way to see the points of the causal set?
So the
points of the manifold or as events on the manifold?
Well, the problem is in the continuum theory, the points or events only have 0 volume. So the idea is to think of the elements of the causal set as having a volume of 1 in fundamental units. So they're something like atoms of space-time.
Okay, so but it's really only the points of space-time, so small chunks of space-time. It does not involve anything like matter on top of it to localize or to these points.
Well, so at the moment, I'm just looking at them as pieces of space-time. We could, of course, define things like matter fields on causal set elements.
So I guess the question is here whether they correspond to the diffeomorphism in their notion of events in space-time as defined by space-time coincidences versus, just points of the underlying topological space of the manifold. So it's basically, I guess, the question was whether, about the physical significance of the events. So about the diffeomorphism in their continuum. So about the ontology of these events.
Yeah, so they're physical entities. They're not, I don't know, in some sense merely points in some topological space. They're real physical objects. And we can imagine defining fields in them. I haven't done that here, but various works have been done in that direction.
Marco? Misha?
So you're saying your second bullet point that the resulting universe in a sense is not like what you would expect to see from GR. So do you think there's any hope that within this approach that you'll get some space-time that emerges that appears like what you see in GR?
Well, yes, otherwise I wouldn't be working on it.
Okay, well that's what I thought. I would imagine, right? I don't know.
So I might imagine that we'll really need a proper quantum dynamics in order to achieve continuum space-time.
So that's the hope that you can just make this quantum, then the emergence theory will be.
Right, that some sort of quantum interference is playing an important role in canceling some of the degenerate behavior that we're seeing from these regulation type causal sets.
And is that kind of the hard part, trying to make this quantum?
Yes, that's challenging. Right, there are many interpretive questions.
I see.
We're not sure how to.
And the last one I would ask is this is the same approach that like people like Rideout are trying, right?
Yes.
It's the same.
Yes.
Okay.
One quick question on this point. About the quantization, you mentioned the path-integral quantization by exponentiating an action. So I've not heard anything about an action or Hamiltonian. Do you have any idea how you would get an action for it?
Yeah, so there's a proposal for the action. There's a paper by Benincasa and Dauker who they observed that so there's a discrete D'Alembert. There's an operator you can write down, defined on the causal set, which mimics the behavior of the D'Alembertian in the continuum. And if you apply this operator in curved spacetime, you can get curvature corrections, which are proportional to the Ricci scalar. And so if you just apply this operator to a constant field, then effectively it's a way of measuring the Ricci scalar of the causal set. And so you can use that to write down an action. And so indeed there does exist an action for causal sets, and some work has been done in looking at the path integral of that sort.
Yes.
Quick
Somehow
one, please.
related, I mean, could you identify local degrees of freedom somehow in causal sets, or do you have any idea how they emerge locally?
So local degrees of freedom, such as a gravitational wave, or well, so I think that these intervals are somewhat local in a way. It's if you want, I mean, a small interval is in some sense as local as you can get in a fundamentally Lorentzian theory. And so if I'm looking at the dimension of one of these order intervals, in a way, I suppose we could think of that as a local degree of freedom.
But do you have any, I mean, with the construction, do you have any constraint actually on the number of the local degrees of freedom, okay, which is some crucial thing?
Well, yes. If we don't add any matter fields to the causal set elements, then the number of degrees of freedom, the number of possible descriptions of an order interval with a fixed number of elements is finite. Of course, it could be quite large if n is large. So, but you might expect that only a tiny fraction of those would be relevant somehow. So if we wanted to measure the curvature in an order interval, then that would be some particular combination of some particular measure of the structure of the causal set in that region.
I guess maybe the question is, do you recover in some sense the fact that you have 2 degrees of freedom per point in the continuum?
2 degrees of freedom?
Yes, for the gravitational field.
I'm not sure.
That could be, of course, emergent, okay, but
Right.
the first step could be just to identify some finite number of degrees of freedom. And also a comment concerning dimensional reduction. I mean, you mentioned that in LQG, low-quantum gravity, and causal dynamical triangulations, that reduction is to 2. This is actually not necessary, okay? In a certain condition, the reduction is to 2, but in CDT, for instance, this really depends on where you are on the phase diagram. It might be 3.5, and other values the same actually in that low-quantum gravity. We wrote a paper on that. And this can even go to 1, okay, in the certain condition, yeah.
I see. Interesting.
But in the physical phase of CDT, isn't it always 2?
Sorry?
Isn't it in this kind of continuous phase of CDT?
Actually, in the continuous phase, the C phase on CDT, it can go to different values. It has been shown by numerical investigations over the last 3 years, actually. So I would say the original result from 10 years ago was that there is 2, okay? And the first paper actually on dimensional reduction in CDT, but then by more detailed investigation has been shown that it really depends on where you are in the phase, okay?
Interesting.
Let's thank the speaker again.